All right, everyone, welcome back. I'm going to actually do video 10 next. I decided to change it so I could do a little bit more with a proof for this derivative. So we'll do video 10's problem set, and then we'll go back and do video 9. No big deal. It's two different ideas, but I like doing the original first and then the inverse function, which is the natural log second. Okay, so first of all, today we're going to do the derivative of exponential functions, but we're just going to start with ones that have a base of e, so e to the x. In the future, we're going to do ones that are like 2 to the x or 5 to the x, or it could even be like 1/2 to the x. But for now, we're going to start with just something basic that we can prove. Okay, so if we were going back to the original way that we found derivatives using limits, this would look like the limit as the h value approaches 0 of the function of x plus h minus the function of x all over h. You should remember that. That's a derivative. So something you would want to note, if I plug in a 0 for h, I do get 0 on top and 0 on bottom, which means there's something I can do. And that something I can do is going to start with me separating these two things. So again, multiplication of like bases means you add. So if I'm adding up in the exponents, I can split them with multiplication. So once I do that, I'm going to factor out an e to the x. And then according to limit rules, I can split this up into two limits because this is multiplication. So I'm going to do the limit of e to the x, and then I'll multiply by the limit of everything else. Okay, so this is a little deceiving because you might plug in a 0 for x and think that this is e to the 0, which is 1, but it's not. Remember, this is plugging in a 0 for h. Since there's no h to plug into, your limit is just e to the x. That's crucial. This part is the part I can't go into here. This has to do with the definition of what the value e is. That comes from doing, if you remember when you did exponential growth and PERT, if you remember that, that's all built in here. But anyhow, this whole thing goes to 1. So basically what you end up with is that the limit does come out to e to the x. So all that's there just for those of you who wanted to see it proved. Okay, and then of course, if you have a function up here in the exponent, you're going to do chain rule because you'd have a function within a function, right? And so you would do the derivative, and the derivative of this would be e to that, and then times whatever the heck the derivative of that inner part was. So we'll also see some chain rule. Okay, so let's try one out. So I've got y equals this. All right, so the first thing I'm going to do is take the derivative of both sides. Here's me showing you that. You don't have to do it. I just like to remind you guys that that's what we're doing. So here is a function. The first function is e. The inside is sine. So the derivative of this side is just dy dx. This side I'll treat as chain rule. So the derivative of e is just e to that same value. And then I do the chain rule, which is the sine, and the derivative of sine is just cosine. So my derivative is literally just e to the sine x cos x, or you can put that cos x out front if you want. Okay, so let's look at this second example. We're going to find when the derivative is equal to 0. So first let's find the derivative. So we've got dy dx on the left. We've got, whoa, check it out, product rule. So we've got x times e to the x. So I'm going to use my product rule. Derivative of the first, 1 times the second, plus first times derivative of the second, which is just e to the x. Okay, there's my derivative. Now I just need to set it equal to 0. Now this is where you're going to start looking for things that we can do to factor. Like I can see that there is an e to the x in both of these. So that's my plan. So I'm going to factor an e to the x out. I get 1 plus x equals 0. Your rule, your product zero product property says that if either part is equal to 0, the whole thing will be 0. So I've got -1. And is there ever a time that e to the something is 0? No. So there's no solutions for this part, which is fine. You already have solutions here. So your only value that would give you 0 is -1 for x. And then this one just wants us to find the second derivative. Okay, so if we're looking for the second derivative, we are going to start with the derivative. And we're going to do product rule yet again. But ooh, there's product rule with a chain rule. So be careful. Derivative of the first, 2x times the second, e to the 3x. plus first x squared times the derivative of this. The derivative of e to the 3x is e to the what it was times the derivative of the inside, 3. So I've got 2x e to the 3x plus 3x squared e to the 3x. That's my first derivative, or y prime. Let's do y double prime. I've got two product rules now. I've got this guy and this guy. All right, let's do it again. So I've got derivative of the first, 2 times the second, e to the 3x, plus first times the derivative of the second, e to the 3x times 3. Then I've got product rule again. Derivative of the first, 6x times the second, e to the 3x, plus plus first, 3x squared times the derivative of the second. It's chain rule. Don't forget that extra 3. Whew. All right, let's see what we got here. We've got 2 e to the 3x plus 6x e to the 3x. We've got another 6x e to the 3x plus a 3x squared. Whoops, I lied. That's a 9x squared e to the 3x. So these two guys are the same. I'll put those together in a moment, but I'm wondering if you guys see that every single one has an e to the 3x, which means for future reference, we probably need to factor that out, especially if we eventually set this equal to 0. Hint, hint, we will. So I'm going to put these in order. So I'm going to use my highest power of x to come first. So if I take an e to the 3x out, I would have a 9x squared. If I took an e to the 3x out of these two, I'd get a total of 12x. And if I took out an e to the 3x here, I'd get plus 2. Again, in the future, hint, 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 if I set this equal to 0, now that I have them separate, I can solve. And remember, there's nothing you can plug in here to make that part 0. So that's nice. You can just get rid of it. But this part in here, this quadratic, you can mess with that. Okay, so good luck with the problem sets. Again, we're going to do them out of order this time, but that's totally fine. And the next time we'll talk about the derivative of the inverse of e to the x, which is natural log.